course, Sue, M0BOZ.
And tonight's talk is builders, transverters, but it's also a look at actually making stuff yourself. Looking at the room, there's very few people who probably haven't made stuff themselves, but anyway, we've kind of pitched it so that all the different skill levels will get something from it, and even if you are not particularly au fait with circuitry and stuff, you'll still kind of go away understanding what a transverter is and that sort of thing. So, right, let's kick off then. So, Sue, let me see if I can make this work. Plug this in this side.
I have to have a crib sheet, by the way, so...
Right,
yes.
okay.
We all do.
So, Sue, what is... Hang on, wait a minute, we're going too fast. Right, that started well. So, Sue, what is a transverter?
Right, a transverter is a transmitting converter.
Well, that's not very helpful. What's a converter?
It's a device that takes a signal found on one waveband and produces a copy of that signal on a different waveband.
Backwards. Right. Well, why would you want to do that?
Right, well, you might already have a nice, expensive, high-spec transceiver, and this is a means of using a waveband that radio wouldn't necessarily work on normally. Something like that.
Without buying a new radio?
Without buying a new radio, sorry. Oh, sorry.
How does it work then, Sue?
Right, do you want me to mix the signals you want to hear with another frequency to produce a copy at a frequency within the range of your existing radio? The process of mixing two signals together to produce a product is called heterodyning.
Okay, mixing signals by adding. You already know this, but we'll go through it anyway. Right, this is a plot of a signal against time, and this part of the waveform, this is a sinusoidal waveform, this part of the waveform, sorry, I've got a laser pointer here. Right, this part of the waveform, I've got to have a steady hand for this, this part of the waveform you can see is the biggest positive value, but this waveform you can see is the biggest negative value. So if you added them both together, you'd get nothing. A little bit further on, and these two slightly different frequencies, you can see this one is nearly at its maximum, and so is this one. So we get a signal that's twice as big. And as we go through this, adding them all up, you end up with a result that looks like this. And you can see, buried in this, that there's a sine wave at a lower frequency. And the frequency of that sine wave is actually the higher frequency minus the lower frequency.
Right, we can demonstrate this. This effect by using sound waves at two different frequencies. So,
You'll love this.
You'll love this. He can't play this. Left hand high. Left hand at the top.
This hand? Right,
Yeah,
okay.
that hand at the top.
It's like being at school, isn't it?
Don't blow too hard.
Okay, I'm not allowed to blow too hard. Right. Okay, so I'm going to play a slightly lower frequency
Yes.
note. Oh, not like that, I'm
Don't
not.
play. Don't blow too hard. Okay. And I am going to play a very slightly higher note.
And if we play them together,
Hopefully you could hear underneath it all that there's that little beat, the beat note. So there you go. But we do have to bear in mind that audio sound pressure waves are not the same as electromagnetic waves.
good, right. Really teach you to suck eggs now. The electromagnetic spectrum, okay, this is a graph with rising frequency this side, and obviously we've got no frequency, this NDC, then we've got audio, radio, you know, all the rest. But
Your dog could hear a dog whistle at 17.2 kilohertz, but it wouldn't hear the SAQ transmitting at 17.2 kilohertz, because one is audio and one is electromagnetic. Right, there is more than one way to view the signals. There's the time domain and the frequency domain.
so here we can see a plot. time moving in this direction, and you can see a sine wave here, which is going quite quickly. The waves are close together, so that's a higher frequency. On this side, we've got a graph of frequency, where the high frequencies are this end and the low frequencies are this end. And you can see this is a fast moving sine wave, so it's high frequency, so it's at this end of the graph. Here we have a second frequency, which is much lower, sine wave again, and you can see that is demonstrated by this spike, which is near the axis of the graph, the origin of the graph, so that's a low frequency. If we were to multiply f1 by f2, then you can see f2 is 0 here, and anything multiplied by 0 will be 0, so the result is 0. Here, f2 is its highest point, we'll call it plus 1, so the sine wave at that point will be multiplied by the biggest value of this, and you can see that reflected in the trace here. At this point we go back to 0, we're multiplying by 0, so we get nothing out. To this side of the graph, f2 has gone negative, so we're actually multiplying the sine wave here by a negative number. So a 1 here will actually become minus 1. So at this point, the resultant signal has actually swapped over to an inverted version of this. This is quite difficult to understand when you look at this wave shape, but if we look at it on the frequency domain, we can see f2, that's still there. We can see the high frequency f1, that's still there. And now we can see that there's two other signals, the difference signal and the sum signal. So that's the difference f2 minus f1 and f2 plus f1.
Right, with frequencies above the human hearing range, or supersonic, it's called superheterodyning. Most analogue radios use this technique and are often called superhets.
It's not a new idea. This is an RCA radio from 1925, and it has portable superheterodyne written on the front. Wow, very impressive. And Clive Sinclair, do you remember him? Yeah. He wrote a book in the 70s called Transistor Superhet Receivers. And here we have a superhet radio from the 1980s. 6 transistors, wow, it's a superhet 6. So very common way of making a radio set.
Right, there are several different types of mixers. As we just seen, mixing can be done by addition in a linear way, but it can also be done in a non-linear way by switching the signals. Non-linear means that the output is not directly related to the input. Oh, is it me again?
Probably.
Yes, it is. Yeah. The single balance mixer, the input signal is alternately connected and disconnected to the output at the rate of the injection frequency, often called the local oscillator, or LO.
Now the single balance mixer produces only the input signal and the two products, sum and difference. Mathematically, the input signal is multiplied by the injection or local oscillator. Now this has the advantage that because the local oscillator is switching the signal, it's effectively cancelled out, so it doesn't appear on the output. So with this type of mixer, you're only going to get 3 signals, the original one and the sum and the difference. Now, the advantage about multiplying it is it increases the output level you get from the mixer, but it also reduces the noise.
Right, so there are also double balanced mixers, where the input signal is alternately inverted and non-inverted to the output at the rate of the mixing frequency, the LO.
Now, this results in only 2 products, the sum and the difference, because effectively both the original signal and the local oscillator are both cancelled out. So that not only gives you more output because it's multiplying the 2, it also reduces the level of spurious signals you get on the output, so there's less to clean up. So Sue, how can we do this?
Well, could use diodes. The humble diode may be used as a high-speed electronic switch to route signals around.
Right, now, a diode, obviously, people know this from rectifying things. If you put the voltage across the right way on a diode, it will be what we call forward biased, and it will conduct electricity. Now, if we apply an AC signal on top of that signal, then when the diode is conducting, the AC signal will also pass through the diode. But if we put the voltage the other way round on the diode, when it's reverse biased, then not only does it stop the flow of any current, block the flow of that current we were switching it on with, but it also, that AC we had on top, also won't pass through the diode. So here we see a double balance mixer done with diodes. And you can see that at the front end here, coming from the antenna, we have some kind of sine wave signal. And this is a transformer, and a transformer will pass an AC signal on its primary, and that signal will appear on its secondary. Now you can see here that's the start and that's the finish, and that's the start and that's the finish of this coil. So whatever's here will also be here in the same phase. The centre tap of this transformer is taken to ground. So with respect to ground, the waveform here is the same as the one coming in. But this winding, the start is here and the finish is here. So what appears here is an upside down version of that input, or an inverted signal. Now, the input from the local oscillator here can be a square wave, and the only thing it needs to be big enough so that the signal that appears here will forward bias these diodes, so about 1.4 volts. Now, let's take the case where the square wave is on its positive part, its positive phase. Then we will have a plus here and a minus here, and that will be reflected on the secondary of the transformer. Now this plus will then appear on this diode, and a diode conducts when its anode is more positive than its cathode, and in this case you can see it is. This is the negative end, and the cathode, you can see this diode is negative, and the two diodes are in series, so they both conduct. Now, as we said before, any AC that's present on top of that will pass through the diodes. And in this case, the normal version of the signal is passed to this point. Therefore, it appears on this transformer and appears on the output. But the local oscillator, you can see half of it in one direction is there and half of it in one direction, other direction is there. So the local oscillator is cancelled out. Now, the input local oscillator changes phase. So now the input is negative and the ground is positive. So now a negative signal appears on the anode of this diode, so it doesn't conduct. But this diode has negative on its cathode, so it does conduct. So we now have a path for that current to pass through these two diodes and switch them on. But now if you notice, the inverted version of the signal is passed to here. That will pass to this transformer and therefore to the output. So if I get this right, there we go, look at that. Look, isn't that wonderful? Right, which way am I going?
I think the wrong way at the moment.
Right.
Right, so transistors are an excellent way to route signals around.
They make very good RF switching devices. But the best advantage of this is a Gilbert cell double balance mixer, a very popular configuration, is that you don't need transformers. And if there's no transformers, you can make the whole thing in silicon and fabricate it on an integrated circuit. And in fact, it's one of the most popular mixers used in communication equipment for that very reason. It's cheap and easy to make.
Right, meanwhile, back to converters. For a practical converter, you will want some filtering to prevent unwanted signals causing problems.
There's three main types of filter configuration. A low pass one, which will block frequencies that are above the frequency you've made it for. A band pass one that passes band of frequencies around that frequency. And a high pass one that will block frequencies below that one. Now, there are many different types of filter you can make using different sorts of components: coils, capacitors, resistors, quartz crystals, ceramic resonators, even glass things used in TVs, amazingly.
Did you mean? Oh, right, okay. The simplest bandpass filter is a parallel tuned circuit.
Okay, and look out for this one later on in the talk. Now, in a parallel tuned circuit, we have a capacitor and an inductor in parallel with each other. If you apply a short pulse of power to this circuit, it will charge the capacitor up. If there's a voltage across the capacitor, that will also appear across this inductor. And the inductor will start to take current and build a magnetic field. And the energy from the capacitor will be used to construct that magnetic field until such time as the capacitor's energy is depleted. At that point, the magnetic field will start to collapse, and when that happens, it will induce a current into the coils. That will produce a voltage across them, and the capacitor will charge up again. So the charge will bounce back and forth between these two, and the rate at which that happens can be found by a very simple formula, F equals 1 over 2 pi root LC. Now this works a bit like a tuning fork, so at frequencies that are too low or too high, this looks like a short circuit, and therefore it attenuates any signals that are not at that resonant frequency. But at the resonant frequency, this all hums along beautifully, and you get a nice big output. So you get taken against frequency, you get a plot that looks like that. If you take the same components but put them in series, now the situation is reversed, and this will allow through any signal that's lower or higher within reason, in an ideal world. But at the resonant frequency of this, all the energy will be taken up in this, and so you don't get much output. Now that circuit is very useful if you have an interfering signal, like a large broadcast band signal, and you want to null it out. You would use a circuit like that. Look out for this circuit later on in the talk.
Right, so a simple amateur station can be realised using a converter.
Okay, now when I first became a radio ham back in the late 70s, there were two classes of radio ham, A and B. And to get the A, you had to do the Morse test, and I wasn't very good at Morse, so I was a B licence holder, and we were only allowed to use frequencies above 100 megahertz. But at the time, transceivers for the 2 metre band were very expensive and hard to get hold of. And I didn't have the money, but Army surplus equipment was very cheap. So I had a CR100, which I can see Andrew laughing over, and I used a converter. Basically took the 2 metre signal at 144 megahertz, mixed it with 116, and one of the results is 28. Now you need a bandpass filter at the front just to stop any big signals overloading it, but for transmitting you have to build your own transmitter, but that's not too difficult, a bit easier than building a receiver. And you need a low pass filter to get rid of any rubbish so that you're not transmitting it. And of course you need a big switch to switch from transmit to receive. And I made many contacts with that. Now, I've also got a certain collection of radios which I've used with converters.
And this, I think, you know, is pretty much the Porchester Radio Museum.
Inside your garage.
Right, well here's one I made earlier. This is a converter I built to listen to the SAQ transmissions, but using my radio on the 30 metre band.
Now, oh, sorry.
Go on.
I was going to say this got me really, really excited. It was so nice to be able to actually hear the SAQ transmission on one of our radios.
Sure. And we're going to try.
Power on. Bluetooth mode.
Look at that. It's amazing, isn't it? It's miraculous. And for those of you who are really into such things, there's a circuit. It's got all the usual bits. It's got a front end. Oh, I must use this push pointer, mustn't I? It's got a front end filter that gets rid of everything apart from 17.2 kilohertz. Now, these filters, they work best when they're lightly loaded. If you put 50 ohm load across that, it tends to blunt the filter rather. So I put a little transistor in there just to keep the impedance nice and high at the front end, and a nice low impedance going into the mixer. This is one of those double balance mixers that Gilbert sell ones, all made on silicon. And then here's the 10 megahertz local oscillator. This actually has its own oscillator circuitry built into it. And oh look, there's one of those series tuned circuits, because 10 megahertz is awfully close to 10.0172. So you want to get rid of the 10 megahertz local oscillator that might be present on the output. Right, I'm going to try now and play you a little video, which may or may not work. I probably should have set this up earlier. Bluetooth settings. Bluetooth on. You have to have an American voice for this, by the way.
Device paired.
There we go, look at that. Look. Oh, it's half off the screen. No. There's the converter down there.
Yeah.
Right, that was it. Hardly worth the bother, was it?
Oh, so worth the bother.
Yeah.
Yeah, it was. So good. Right, meanwhile.
Right.
Oh, sorry, me. To make a transverter, we need to make the mixing process work one way round for receive and the opposite way for transmit.
Keep going.
Oh,
Oh, all right, I'll do it.
Oh,
Okay, most ham radios put out quite a lot of power. Even an 817, the minimum setting is half a watt. And that mixer chip doesn't need anything like that. So we're going to need some way of reducing the power coming in from the transceiver you're using to a level that's suitable for, hello, I've got a hand appearing here.
What?
How do I get rid of that? Excuse me, right. Yeah, to make it suitable for the mixer, to stop it being overloaded. You're also going to need a power amplifier so we can be heard on the air, and of course one of those low pass filters to stop all the harmonics causing problems.
Right, so, sorry about this. The ideal transverter allows you to use your radio as normal with a little magic box to perform the transduction.
So, what's inside the magic box? Well, in this case we've got that same setup, a 144 meg antenna and a 28 megahertz transceiver on the 10 meter band. So, what's inside the box? Well, when we transmit, we need something that's going to detect that we're transmitting. So we need something to sense that there's RF there and switch this circuitry over so that it's in transmit mode. So that detects it. We then go through the power attenuator, as we mentioned, to reduce the level, into a mixer, but the mixer now has to be able to go both directions, be switched round either way. We need a power amplifier, and we need a switch to route the signal through the low pass filter, which is there to get rid of harmonics of that transmitted signal, and onto the antenna. Now, when we let go of the PTT switch or whatever, go into receive mode, this needs to detect that, switch the thing back. Now the signal from the antenna comes through the low pass filter. Well, it doesn't need the low pass filter, but it doesn't really do any harm, so why switch it out? It then needs to go through a really good band pass filter, and that's what really makes a good receiver, is that band pass filter. The better that is, the better the receiver's going to be, the less weird stuff's going to come out that isn't really there. Now the reversible mixer has to go the other way. The local oscillator, of course, is being used the same for both, and that then feeds the signal into the transmitter that you're using this thing on.
Okay, a transverter is a good way to get active on the MF amateur band, for instance 472 kilohertz. You can use your existing HF transceiver, and if you already have a data connection, you can also use Whisper.
It's also a great way to use up all those bits in the junk box. But as Churchill said, to be successful is to remain enthusiastic despite repeated failures, and that is very, very apt for homebrew radio.
So, how to get started? The way to attempt a project like this is to break it down into functional blocks and build and test each block one at a time.
You're going to learn a lot by doing this, and you're going to have a great deal of fun, if that's your idea of fun. Homebrew is a cross between a crossword puzzle and needlework. But when it works, wow, it's amazing. Often you can find suitable designs for these functional blocks, either on the internet or read a book, gosh. And you can often adapt those fairly easily to whatever function you want that block to perform. So, here's my 472 kilohertz transverter as a block diagram. As we've said before, in the transmit mode, we come in through a power attenuator. Now, the mixer chip already has a big amplifier on the front end, and you can't get rid of that. So I've actually had to attenuate the signal more than I would have otherwise done, but it doesn't really matter, it's easy enough to attenuate stuff. We then mix it with a local oscillator, 3.2 megahertz, you'll see why in a little bit. It goes into the mixer. Again, this is a double balance mixer, so we only get the sum and the difference out, the other two bits have gone. But we need a filter here because there will be a different signal here. So we'll get the 80 meter band, 3.6 megahertz minus the 3.2 will give us the 400 we want. But of course there'll also be a signal which is at 6 point something megahertz, which is the sum of 3.6 and 3.2. So we need a filter to get rid of that because we don't want to be amplifying that and using up a lot of power to do it. We then need some kind of drive to boost up the output suitable for a power amplifier, and then we need a low pass filter. I've chosen 800 kilohertz because the second harmonic of this will be at 940 or something, so 800 is a good compromise to get very little loss at this frequency but get rid of all the harmonics above. And of course we're going to need a receive. We're going to feed a signal into here. Again, we don't need to switch that out, it doesn't make much difference. Into our nice big filter that's going to get rid of all those broadcast stations and other nasty stuff. The mixer nicely has this big amplifier now, which is very good because we can get lots of signal. We're going to mix that, we're going to put it into some clipping protection. Now why do we need that? Well, when you transmit, there's a slight time difference between the transmitted signal appearing and all that switching circuit, switching it all over. And while that's happening, the transmitted output is potentially connected to this mixer. So you really want some way of making sure it doesn't blow the mixer up while that little switching process takes place. So we've got a little clip protection circuit in there.
Right, so why so many filters? The signals on 472 kilohertz will be small, but not far away, of course, are broadcast stations with massive signals.
Without adequate filtering, the mixer can easily be overloaded and you'll get all sorts of weird stuff appearing at the output. There's a lot of filter designs that you can use, textbooks are full of them. Each has different pros and cons. I started with simple filters, but I quickly realised it wasn't going to work. And as with all these things, the design grew, and of course with hindsight, it could be done a lot differently.
And so what waveband to convert to? It doesn't matter, but higher frequency circuits are hard to build as the lead lengths must be kept short. Lower frequencies, of course, need bigger coils.
And of course, ideally, you want an output frequency that's not a harmonic of the input frequency. Otherwise, you will end up with a giant oscillator. I chose the 80 meter band. 3.5 megahertz is a great compromise. It's very easy to work with, and very cheap test equipment that you can find at any junk sale will measure 3.5 megahertz.
And then it's choosing what frequency. To make tuning easier, you want an LO frequency that displays a frequency on your radio that is easily related to the actual signal you're receiving.
Now, you might think, oh, 3 megahertz. That would mean that 472 would end up as 3.472. The problem is that's out of the 80 meter band, and most transceivers won't transmit on that. So I ended up with 3.2 megahertz. You'll see why in a minute. And that means that 472 appears on my radio as 3.672. But of course this MF band is very, very narrow, so you never actually ever get out of, well, even the first digit, really. So it's not ideal, but it's a usable compromise. And the difference product that we'll get will be at 2.728 megahertz, which is, if you work that out. So that's not going to be a big problem for your receiver to get rid of. Okay, so here's a circuit of the finished thing. My God, that looks horrendous, doesn't it? But as we said earlier, break it down into functional blocks. So let's start with the local oscillator. Now, 3.2 megahertz crystals are not readily available anywhere. I certainly don't have any in the junk box. But I got a load of 16 megahertz crystals and plenty of old logic chips. So I had a cunning plan.
So, if you divide 16 megs by 5, you get 3.2 megs. You can get a divide by 5 chip, 7490, but the output is a pulse every 5 counts, no good. So then use a counter preset to 15. After 5 counts, 15, 0, 1, 2, 3, the third binary output, QC, goes high and it resets to 15 again. The second binary output, QB, has a nearly square wave output at a fifth of the frequency. So a bit of filtering gives a pretty good waveform.
So here's the circuit. All these circuits you can find on the internet. This is your basic Colpitts oscillator, crystal oscillator. If you put in 16 megahertz crystal Colpitts oscillator, you'll find that circuit. I put a little buffer on there, and it needs to be at logic levels. These things run on 5 volts, so you need to make sure the signal is 0 and 5 volts coming out here. This circuit is the presettable counter, like what Sue just told you. There's a little bit of logic around it because the signal needs to be the other way up to operate the reset. The output from that QB, as Sue said earlier, that I'm feeding into, oh look what this is, your bog standard parallel tuned circuit at 3.2 megahertz, as mentioned earlier, to nicely get rid of everything else. And that actually goes to a buffer, but I haven't bothered to draw that on here. Now, there's massively easier ways of doing this, but boy, it was great fun, and I had all the bits, so why not? And that's what it actually looks like when it's built up on a bit of old board. Thank you, junk sale. Here's the crystal, here's a little trimmer, just to make sure it's absolutely spot on, because 472 kilohertz band is pretty, you have to be pretty accurate. And this crystal, it's got a 5 volt regulator. Now, the stability of the crystal oscillator is much better if you can provide it with a really good supply. And obviously, if you're using whisper, you do not want the frequency to wander about. That's the oscillator transistor, that's that buffer transistor, that's the little filter circuit, that's the inductor and some capacitors that generates the 3.2 megahertz bit, and that's the binary counter, the preset counter. Okay, so now the receive bandpass filter. Now, that's there to only allow through the signals on the wanted band, and of course we've got broadcast band signals on 1 megahertz in that region, so not that far away. Now you can find a lot of free filter design tools on the internet, and you can get lots of different layouts of filters. I chose a Butterworth in a bandpass configuration, and I fed the numbers into the design tool, and it gave me a lovely thing at 900 kilohertz. It's attenuated by 50 dBs, absolutely wonderful. And here's what this website gave me. All the values, absolutely marvellous. And look at that, absolutely fabulous. So I built it and it didn't work. I carefully wound all the inductors and used my eBay inductance meter. Of course, what you have to remember is that inductance meters measure at the frequency they work at, not the one you're using. So the fact that the inductance meter tells you something doesn't mean that's what's actually going to happen. So I broke out the junk box and had a look in there, and I had some IF transformers, some intermediate frequency transformers from an old transistor radio that were pretty close. So by fiddling around, I got it to work. I got exactly the sort of rejection I wanted. And that's what you have to do. So here's what I ended up with. Here's the two things torn out of an old radio that was in the junk box. And here's some values I came up with. I had to put a trimmer in just to get it right, to tweak it up to the right thing. And these are all adjustable, so I had lots of opportunity to play around with it. Right, the low pass filter. Once again, this is there to get rid of any harmonics of the transmitted output. Now, it makes sense if you're making projects to make everything 50 ohms if you can, because then it's much easier to test stuff. Signal generators tend to have 50 ohm outputs, so if you want to test things, that's a good thing to have. Remember, harmonics are always higher in frequency. There's no such thing as a sub-harmonic. Now, I chose a nice Butterworth filter, and once again, I used that wonderful design tool. Bang, there it is. Put all the numbers in, and it gave me all this wonderful stuff. And I tried it, and it didn't give me as much rejection as I wanted. And part of the reason for that is because the driver thing wasn't actually producing 50 ohms. So get what you rubbish in, rubbish out. So with that, I noticed it wasn't attenuating the third harmonic as much as it should, so I just increased the capacitor values a bit and played around with it until it did. And here it is. Two toroids, I think they probably came out of some switch mode power supply from a PC or something, wound up and measured on my inductance meter, and some capacitors jammed down the back here, a load of stuff all put together to get the right values. Okay, now the transmit bandpass filter and this double balance mixer circuitry. Now, the transmit bandpass filter is there to clean up the output of the mixer. As I said before, you get two outputs from that mixer the way we're mixing it, and the other one will be at 6.8, so it doesn't actually have to be a terribly good filter to get rid of that. I chose a simple parallel tune circuit for that, and that's sufficient to get rid of the spurious signals. The double balance mixer is a Gilbert cell chip, like we mentioned earlier. This one's made by Plessey. It's an SA602, much loved in communications equipment over the years. It's got this front-end amplifier, which is really good because that means you detect very sensitive receiver that will give you nice output on very small signals that you might find on 472. Now, obviously this has to go in one direction for transmit and the other direction for receive. And I've used analog switches for this. Relays are okay, but the contacts can get dirty and they can become unreliable. Analog switches never go wrong unless you overload them, in which case they blow up very well. So ideal for using around a mixer where the signals are small. And that's that little parallel tune circuit bandpass filter, that same old configuration you've seen so many times. And here it is. There's the analog switch, there's the double balance mixer, and there's the little filter circuit, and also a voltage regulator. For the bigger signals, like the output from the transceiver, I'm using relays, because obviously they're bomb-proof, they're not going to blow up if you put big signals into them. Right, and you'll also notice there are a lot of coax around that, because that's where all the switching happens and it goes off to all the different bits. Okay, the transmit attenuator, the front end attenuator that's going to absorb all that power from your transceiver. So one more input from the transceiver, you've got to reduce that, so we basically have a couple of pi network attenuators. Now the first stage is going to have to absorb a lot of power, the second stage less so. And that is the wire that goes off to that sense circuit that's going to detect when we're transmitting and switch everything over. So, 2 pi networks for 50 ohm impedance. You can see this big power resistors here, and you notice I've already forgotten to switch the transceiver down before I fired it up, and it's gone all black where it's cooked itself. And there's the relay, which is doing the power switching. Okay, the transmit drive amplifier. So you've got very small signals coming out the mixer, and you need to boost those up to drive the power amplifier. So basically what we've got here is a pre-amplifier stage, which actually I pinched from a hi-fi I made millions of years ago, hence the BC109. The BC109's worked up 600 megahertz, so it's fine at 472. And here we have a tuned amplifier. Basically, there it is again, that little circuit, parallel tune circuit in the collector. And I've actually taken what I found in the junk box, got a bit hot, so I put 2 of them together. So it's actually 2 transistors wired in parallel with each other, and a big heat sink to dissipate any power. And there's the tuned circuit. The power amplifier, well, This is what happens when you have a junk box. Because a long time ago, I built a MOSFET power amplifier to use with my FT817 when I was away, using the IRF FETs, which a lot of people I know in the club have used. And this isn't my design, I pinched it off somewhere. And it didn't work, as these things don't. It really didn't give much out above 80 metres. So it went back in the junk box, and then I thought, oh, that would be brilliant for 472 kilohertz. So out it came, and the only modification I made was to add a bit of extra capacitance to the output just to stop it whistling at too higher frequencies. But it was already made, so why not use it? You could probably buy something off the internet if you wanted to do that. So, the last bit, the input clamp and the TXRX sensing circuit. So, here's that feed-off that you saw on the previous diagram. It comes down to a little diode rectifier here. When you put RF power in here, this has a DC voltage coming out of it. The RF is turned into DC, and it charges up this capacitor, operates this transistor and makes the relay go, which switches over the big signals. But of course also we've got those analog switches, so we've got a little bit of extra circuitry here just to limit the values, because those things work at 5 volts, whereas we want 12 volts for the relay. So all that is the switching circuit. That's what's going to make it automatically change over to transmit when you hit the PTT switch. Yeah, and they're actually active logos, but it's irrelevant. Right, and obviously you can see a lot of coax cables coming in and out of this bit, again, because this is where a lot of switching happens. And the clamp circuit that I talked about on the input to that mixer, so to absorb that power when you first hit the button before that switch circuit has a chance to change, that's very simply 2 diodes back to back, and that will limit the input to 0.7 of a volt. So that's the complete circuit, and now you know what all the bits do. It looks nice and easy, doesn't it? It no longer looks like that horribly intimidating mass of stuff. So there it is, it's a whole thing. I would show it to you, but it's in a container somewhere and I cannot find it anywhere. But you can see all the main bits there, the filters and the power attenuation, all the rest of it. And it actually went into a box. Wow. So, when you first look at the finished result, it looks absolutely frightening. But I hope we've shown that if you tackle these things in easy stages, you can both achieve them and understand them. Things don't always work, but I think the journey is as much fun as using the result. So here's hoping we might have inspired you to do some homebrew now. Thank you very much. Dare I ask if there's any questions? It's all right, Andrew's sitting here, he'll answer them.
They've all fallen asleep now.
The double balance mixer you're using, why did you go? What's the benefit of that over a passive component?
It has the amplification. It has 20 dBs of gain at the front end, which is great. In the converter I made for SAQ, it's got all the oscillator circuitry in there, so it's very simple to use. And I had them in the junk box. I bought 10 of them on eBay, so I had 9 left over. So what are you going to do, you know? And it's got relatively few components. If I'd used the diode thing, I would have had to make 2 matching transformers and carefully wound them so that they were all balanced on that.
I see, yes.
And if we whiz back to that, back to the dark ages somewhere, you'll notice here it's actually got a pot you can put on it to balance it up. So if it's if you're getting anything out, any of the 2 original frequencies, the local oscillator or the input, you can adjust that pot to balance it up, so nothing comes out apart
So
from
you
product
just get the
and
sum in the product. Yes, neat.
Yeah.
So you'll be selling those off at 10 times the price.
Well, I have noticed that they are being advertised in surface mount form. Whether they're actually what they say they are, or it's just the Chinaman has, because unfortunately, along with some of those toroids that I bought off eBay, when you wind them, you find they're not what they say they are. So, yeah. I haven't actually plucked up the courage to buy a tube full of the the surface mount ones and find out if they're actually what they say they are. Any other questions?
What aerial were you using to hear the SAQ when you used that? Because it was so clear. I tried and I could just
Yeah.
hear it in the noise.
I think that's
Yours
year
was
3
fantastic.
of that project. Year 1 was, I think I can hear something in amongst that horrific noise. I was actually using a G7 FEK, which is an 80-metre antenna, with both the sections connected together as they are, with a large loading coil put on it. But I do have a very good earth mat in the garden. But
Well, you did have.
Did.
I did have, sorry, I did have a very good earth mat in the garden. But the one thing I will say is front end filter. It's that bandpass filter at the front end of the receiver. That's what really made the difference, spending some time getting rid of everything else apart from 472. And the sharper you can make that. Sorry?
You said 472, it's 17.
Sorry, 17. Yeah. Yeah.
Yeah, brilliant.
Anyway,
Thank
yeah.
you.
So yeah,
Really good.
persevere.
It was
But make
worth
a
it.
decent front end filter. What were you using? A transceiver?
It was SDR play.
Yeah, yeah.
So,
I mean that
you know.
probably should work pretty well, but
Yeah.
of course they're very wide band, so you need to make a really good front end filter if you want to have a good stab at it.
Okay.
I mean, I was amazed by the results I got from that. I was absolutely gobsmacked when it came through that clearly.
See, I didn't get. I'm not getting good results with a low pass filter. So the band
No.
pass filter seems to be a much better
Because there's
idea.
submarine transmissions very
Yeah.
close to that, and I really had to peak that up so that the submarine transmissions were on the skirts of that wave shape. No?
Right,
Well,
okay.
You've all fallen asleep. That's amazing. Okay, thank you very much indeed then.
Thank you.
Thank you.